Hi, Jake from Bush&Bush Coffee Systems. Welcome to part 3, the final presentation of pressure and flow in espresso. In part 1, we looked at pumps and pressure. In part 2, we looked at restrictors and their role in creating flow. Today, we want to look at coffee in the filter basket and examine the roles of pressure and flow. We're all familiar with the portafilter basket, and when loaded, they obviously look like this. We call this the puck, and they can be wet or dry depending on pre or post extraction. A great way to think of the dry puck is like this glass of marbles. Let's imagine that each of the marbles is a coffee particle. They obviously touch each other, but also spaces exist in between each marble. These spaces interconnect to form a maze of galleries which go from the top all the way through to the bottom. Now, coffee particles are not perfectly round and they're not uniform in size, but the structure of the puck is porous and there is a maze of galleries. The size of the galleries is directly proportional to the grind size. Coarse grind, big galleries. Fine grind, small galleries. It is the role of pressure to motivate the water through all the galleries. The objective of water is to get out, seeking the lowest point through the path of least resistance. The water does not seek the coffee particle, it seeks a path around it, like water flows from the mountain down to the valleys to the ocean. If the galleries are large, less pressure is required as motivational energy to overcome the friction of all the twists and turns. If the galleries are small, more energy or pressure is required. So if the water is avoiding the particles, what's going on? Roasted coffee is a porous product. At a micro level, it is full of tiny fibrous tubes. The coffee particle exercises a natural phenomenon called capillary action to draw water into these fibrous tubes. This phenomenon is utilised extensively throughout the natural world, and many engineering principles rely on it as well. It is known for easily overcoming gravity. The rate at which the capillary action occurs, though, is directly associated with the fibrous makeup of the roasted bean, and this was created during the roasting process. Coffee roasting is the transition from green beans to roasted beans. And at Bush&Bush Coffee Systems, we've developed very accurate methods of measuring that roasting effect on the bean and can translate it to the capillary rate. In broad summary, lightly roasted coffee has a tight fibre structure and a slow capillary rate. Dark roasted coffee has a more open structure and a faster capillary rate. This is where flow becomes important to extraction. While pressure motivates the water through the puck, the flow rate is the speed at which the water travels through the puck. The rate at which the water flows past each particle determines the effectiveness of the capillary action in each particle. If the water travels too fast, the capillary action cannot compete and under extraction will occur. If it travels at the correct rate, the coffee particle will take up only the correct amount of water required for extraction to occur. This defines espresso as percolation instead of immersion. We can observe the capillary action for ourselves here in this portafilter that has been sitting in water. We'll conclude by observing a shot in our test machine, the Noble, where we've matched all the fundamentals. We will observe the pump pressure gauge rise to the limiter setting and then the puck pressure gauge rise to almost match the pump pressure, at which time the shot will appear and then drop marginally as the puck expands to fulfill the extraction chamber and subsequently increase in gallery space, reducing pressure. Importantly, the two pressures do not match, and so obviously free flow rate was maintained. Thanks for joining us. Look out for our next series where we venture into the density technique and start testing coffee. Let's not forget, it's all about the coffee. Cheers from Bush&Bush Coffee Systems.